Python library for parallel computing in Python. It is designed to parallelize libraries like NumPy, Pandas, scikit-learn, and many others. So show of hands, who has heard of DASK? Okay, that's new. Who has used DASK? Oh, that's actually also surprisingly large. Well then, this talk may be kind of boring for you all then. No, that's not true. Lots of fun. So Python is slow. DASK scales out Python. So happens in a few different ways. Using tabular data, you might arrange many pandas data frames across many computers. That'll give you a DASK data frame. DASK is just coordinating many pandas data frames, giving you sort of one large logical thing. In this way, it extends very much the existing libraries in parallel. Similarly, maybe for more importance in this community, there's Dask Array. Dask Array provides a parallel variant of NumPy. It looks and feels a lot like NumPy. It also uses NumPy under the hood, and it scales out nicely across a cluster. So if you had, for example, say many TIFF files across an HPC machine, or just your local machine, you wanted to operate on those either on your laptop with the data set is larger than memory, or in a cluster, if you want to pull up 10 terabytes of image files, Dask might be a good tool to help you do those things. So what I'm going to do is I'm going to show a couple of slides that I've just shown. I'll show a couple of examples with Dask Array, and then if things work out well, I'm also logged into Xiongtao's cluster. Xiongtao's in the back. You want to wave briefly, Xiongtao? He's up at the Advanced Bioimaging Center up here on the top of the hill. And we're going to sort of play around with a Slurm cluster and Dask Array and some imaging things. We were frantically getting that to work in the back of the room during the last talk. I apologize, I didn't hear your talk at all. But so we can play around with things. That might be sort of fun to see Dask on a cluster, dealing with image data, and we can just fool around. That'd be fun. Has anyone ever people who've used Dask on a cluster? So, okay, so that's great. So everyone else is using Dask on their local machine, on a laptop. That's really common. Maybe now it's also fun as we can play with Dask on a larger machine, and that'll be fun to see. I'm just going to quickly put up a stopwatch so I know when I should get off. Great. So let's start. Actually, oops. So if you haven't ever seen it, Dask Examples has a bunch of fun examples. It's a nice place to play with Dask, or play with Dask arrays. And I'm also going to launch this as a binder. So if I'm boring, you can go off and play on your own. So I'm starting up just a really small container. And we're going to play with Dask arrays. So again, Dask is going to coordinate all these little NumPy arrays in parallel across a single machine in this case. And then in a moment, we're going to switch to a cluster. We're going to have sort of intuition for how Dask array works. So let's yeah, so here's my array. It's a 10,000 by 10,000 array. So this might be like a really large image, or a modest image. And we're cutting it up into smaller arrays. Should it be even larger?
Is it possible to make the text bigger? Oh, yeah, yeah.
Like that?
Yes.
Yeah. Great.
That's bold.
It's a pre-canned example, so less bold, on a Docker image running on the cloud. So I can just hit Shift-Enter, and it's totally fine. And so I can do normal NumPy-like operations on that Dask array. So I'm adding it to its transpose. I'm doing some slicing. I'm taking a reduction across some axis. And I got some other array. And again, that array is, again, composed of many smaller NumPy arrays. Nothing has happened. Dask is lazy. As I call compute, the sort of 4 threads on this machine go to work computing all of those things. So what Dask did is it constructed a TAS graph from this bunch of arrays and this set of computations. And this is that TAS graph that it generated. That may not be highly visible, but hopefully you can see that it looks kind of messy. So every little point there is some NumPy function that gets run on some thread of this computer, or if I had a cluster, on some core across one of my machines of my cluster. So DASK array is breaking up that large array computation, lots of small ones, and then running them in parallel. What we're seeing here on the right, when I call compute, we're seeing the activity of each core of my single machine operating over time. So every line corresponds to one thread, and every box corresponds to some NumPy function. So at the left, it's making a bunch of random data, so we're calling the NumPy random functions. That takes around 70 milliseconds, 100 milliseconds. Then there's some adding and some slicing. Those are these green boxes, and they're taking 100 milliseconds, and so on. And we're just doing a bunch of that. Let's see that also. Oops. I'm going to run that again, and we're going to see the TAS graph. So this is the same graph as this graph, where now we're seeing it live. This gives you a sense of the kinds of execution that DASK is doing over time. So DASK is a live system. It's running and controlling all these things. People who have used DASK, raise your hands again. Keep your hands raised if this is new to you. Okay, so people haven't seen this kind of diving in, it seems like. Okay. It gets way more fun when you're on a cluster. So now we're going to play with actual image data. This is from a sequence of blog posts written by John Kirkham, who's not here, unfortunately, and also Matt McCormick. If we get, I actually just copied the ITK cell. We're going to see if it works. It may not work. Yeah, so I'm on a Slurm cluster up the hill, and there are a bunch of images. I actually don't know any imaging stuff, so I assume you all know something about this data. I don't. But I have a bunch of TIFF files. I've got around 600 TIFF files. My understanding this is a common situation. You have a big bucket full of TIFF files that correspond to some chunk of some larger data set. I'm going to use just normal scikit-image. I'm going to look at that data in a few different dimensions. So this is a 3-dimensional TIFF file. And I actually don't know what this is. Xiongtao, what is this data? I mean, scientifically, what is it? Do we know? Or can anyone identify this image?
About maybe the trafficking, the labeling of some memory proteins. So it monitors the trafficking process.
I'm going to assume people, protein expression, I'm going to assume you guys know what that means.
Yeah, protein.
Great.
Yeah.
It's biology. Here's science. Science is on the screen. This is one image and just slices out of that one image. Each chunk here is like a few hundred megabytes. I've got 600 of those. I can't put those all into my laptop memory. So I'm going to use DASK array and scikit-image together, and I can easily sort of construct DASK arrays lazily by saying each task is reading some file, and then let's arrange those various files into some organization. I have to tell DASK how to arrange that, but that's fairly easy. So here I'm pretending I'm arranging it along the first axis. So every chunk here might be one 3-dimensional thing, and I'm sort of stacking them on one axis, or I might stack them across a different axis. It turns out this data is actually arranged in a much more complex way across a couple different axes, and that code is here, but I'm not going to go into. But I was able to represent a much more complex mapping of those different file names into their placement in this 5-dimensional array with Python code. This is something that someone who's not particularly trained in DASK can do. So they had a complex naming scheme. Let's go look at one of those file names again. So someone wrote some code that looked at all of these things and said, oh, those probably correspond to where they belong in this sort of larger array. And then they assembled sort of an array of arrays and placed each file name in those, then loaded those with DASK array. So this is all just sort of metadata. And we've constructed this large, not too large, actually, a couple hundred gigabytes only, but this large DASK array. It's completely lazy. If I were to load this locally, I would run out of memory. So I'm going to connect to a cluster. And hopefully in just a moment, we'll see some workers spin up. So I'm connected to a Slurm cluster. Slurm is like PBS or SGE or LSF, if you are familiar with one of those. It's a way to manage many machines. And I'm asking for 10 machines. So now, I've got 240 cores and 5 terabytes of RAM that I can play with. So now we're just going to play with this machine on this data. We might do something simple, like take this big array and sum up all the numbers in it. So we're going to do that. So DASK broke that down into a couple thousand tasks. So now rather than 4 lines up here, we've got 240 lines. We actually didn't even get all of them. There aren't enough tasks to saturate my machine. Every little horizontal bar here corresponds to mostly reading scikit image data. We're mostly just calling scikit image imread. That's nice. Yeah, go ahead.
Handled behind the scenes that which machine's memory loads which data? Or
In this
do you
case,
have to?
no, we didn't give it any of that information. We could have given that information we wanted to, but I assume that in this machine there's sort of a global network file system, and there's no real data locality between the nodes and the data, which is pretty common.
But doesn't each machine have its own RAM?
Yes.
So you don't have to specify to load certain files into the RAM of certain machines. That's all just handled?
That's correct. So DASK will handle that. It will then track the RAM of all the machines. If one machine is running out of RAM, it'll make sure not to load more data there. If some computation needs to be run on some chunk of data, it will know which machine has that data, and it will run that computation there.
Cool.
Yeah, it's great. So we computed the sum of a big array. And
Sorry, just a quick question.
Yeah.
So when you run stuff on the Slurm cluster, do you normally run things in Jupyter notebooks like this, or just as executable files?
both.
Because I run things as executable files, and this is insane. Like, you have a function just connecting you to the Slurm cluster here. Like,
Yeah, that's great. I can do this, and things run. But so here's where we run into problems because I didn't actually prepare. Zar isn't installed yet. So I'm going to store this data as Zar. It's a file format that I like and find efficient. And what's nice here is that DASK isn't making image reading functions. We're using scikit image. And we're not writing file formats. We're using Zar, the sort of other library that exists. And it's building a wheel because I use pip rather than conda, which I feel silly now. But if that finishes, then we can keep going on, and we can store that data to Zar. And after that, if I install ITK, I can't install ITK, it should work out. I can use ITK on this big image. And I can do deconvolution in parallel across this large machine. And that'll be fun. So now, is there any other questions while we wait for pip? It ran. Great. Let's store the Zar. Look at that. Oh, no. So this is where the live coding thing comes in. No module names are. Yeah, OK. Well, let's see. So I don't have the PSF yet. Anyway, this is a good point to point you to the DASK blog, which has all of these things running more properly. So this is all taken from a couple of posts on loading large image data with DASK array, and then using DASK and ITK together for large image analysis. So I work at NVIDIA. I mostly just work on DASK. We are working people like Kitware, mostly just Matt, and people like Xiongtao and Gokul here to try to make these workloads a little bit better. And we're writing about it, and you may want to engage in that process. Let's see. My guess is I just don't have this file around. Matt, is that likely true? Is there anything that I can do to make the ITK stuff work right now?
It's the same data folder?
Could be, but I'm just going to make...
Did the pip install succeed?
It did, but the workers have already tried to import Zar, and they're just Python processes, and so they still don't know where Zar is.
You can restart the first year.
Yeah? Yeah, got it.
Just created a very interesting one.
Let's see if that works out. So we're reading the data in again. We are then, no, so we're getting a bunch of errors. So these little black things correspond to errors. So something's wrong with my ITK code. And this, again, is me being unprepared, and I apologize for that. But we can use libraries like DASK together with scikit-image, together with ITK, together with PyTorch. We can run it on a Slurm cluster, and DASK is providing a lot of that administrative parallelization effort while not providing a ton of requirements or constraints about what you run with it. And that's nice. We get to reuse a lot of our existing systems, a lot of our existing software and workflows on these resources that we already have. Who here has access to a cluster of machines through an institution that you don't use? Yeah, there's still quite a few hands. So anyway, that's DASK. And that's DASK and imaging. Maybe going to stop for questions, or we can just break early. Any other questions?
Any questions for Matt Rocklin?
Great.
What over here?
So I have a question about DASK arrays and how to use them, if there's sort of like guidance on how to use DASK arrays. Some things work really well because they're already implemented there. But now if I need to write some funky NumPy code that does something that's a little different and is a little bit ad hoc, what's sort of the guidance on how to do that so that it really works fast on?
Yeah, that's a great question. And we're kind of running into that same situation here with ITK, right? There's no DASK ITK module. We had to sort of take ITK, take DASK, and try to throw them together. And the blog post goes through all the pains we ran into in doing that. I recommend looking at it. So there's functions like map blocks, which takes your function and applies it in an embarrassingly parallel way to every chunk. There's other functions like map overlap. Maybe you have data that needs a little bit of sort of neighborhoods across your different blocks. And DASK can give you those sorts of primitives that allow you to run your own Python function on top of those tasks. So there's many sort of common communication paradigms built into DASK array to make it sort of easy. And sort of make it easy to compose with your existing code. Sometimes it doesn't work out. You can also take all those individual blocks and make them little small delayed NumPy arrays and do whatever you want to with them and then go back to DASK array. There are many ways of going in and out of sort of the DASK array paradigm designed to sort of with your exact use case in mind. Does that sort of answer your question?
Yeah.
Okay.
One last question.
It's really great. You can completely automatically do all these things. I'm quite excited. So I'm experienced with OpenMP, and I know there I had a lot of problems. If I do something wrong and I get access to the same memory, it was much, much slower. So I guess your tools are implemented for some things which were great and you can parallelize, but sometimes it probably not. So I'm just wondering, is there any custom controller where I can decide what is parallelized, which memory is duplicated, I mean, which variables, or it's all hidden and it's just, if it works, it works. If I have a problem where I have access to the same memory, then I cannot change it.
Yeah, it's a good question. I'm going to answer that in two ways. One, DASK is definitely higher level and lower performing than OpenMP or MPI. Those are going to be much more higher performance if you want to do hardcore, low-level, fine-grained parallelism. DASK is not a good library for those. I am going to show you quickly an example with DASK futures. I'm off at 10 minutes, right? I got a minute left? Great. So I showed you DASK array, and that's parallel NumPy. But that's built on top of a lower-level thing called DASK. And DASK has been used to parallelize many different systems. And there are a variety of low-level APIs that you have access to, which just say, like, run this Python function over here, run this other Python function over here, run this function wherever it makes sense, make sure the data ends up there. And so DASK can be much more low-level, allowing you to execute sort of arbitrary Python functions anywhere. You can build a variety of things through this. Let's see if... So the sort of simple way to do that is with the futures interface. Here I have some simple Python functions that sleep and they do a small amount of work. I can run them locally, or I can run them remotely. I can submit that job to run somewhere. Here I'm submitting one small Python function to run somewhere. And it ran. There's one little task here. And I can give the result back. I can chain dependencies by submitting tasks on each other. So this isn't DASK array. I'm just like saying, run this function, make that happen somewhere. And I can do that many times. I can build up a for loop of many of these things. And I can easily use, with more custom workflows, all of my compute resources. And I can scale those resources up also dynamically and get more parallelism. So this is an API. I ran through that really, really quickly. So I don't expect people to actually understand what I just said. But hopefully this code looks not like DASK array. It looks not like NumPy. It looks like just submitting small functions. And that's something that you can use to build up more custom workloads. And so again, if you want to look at that or learn more, you might go to examples.dask.org. There are many examples here that might speak to you. And you can run these exact same notebooks there. So thank you all for your time. Thank you for the opportunity to speak.